Now our next subject is going to be to look at reflection and transmission of electromagnetic plane waves at the boundary between two different media. So what we're going to start from are the boundary conditions that, that we've seen earlier when we did electrodynamics and matter. So essentially what you do is that you just take the Maxwell equations and you remember either you use Gaussian pillboxes around the boundaries or you use Ampérian loops. You use divergence or Stokes theorems to write the conditions on the perpendicular and parallel components of electric and magnetic fields at the interface. So once you've done that, you obtain these conditions here. So the perpendicular component of the electric fields is just modulated by, if there was a boundary surface charge, then that would appear on the side here. Here at the interface, we consider that there's no surface charge or no surface current. So all the source terms on the right-hand side are vanishing. If we have two different media, 1 and 2, with different permittivities, then Gauss's law tells us that the perpendicular bit has this this behavior, this discontinuity. For the magnetic field, of course, there's just nothing happening because we're again looking at a situation without sources. These equations here are also quite simple. The parallel components of the electrical field are continuous. The parallel components of the magnetic field are a bit, like the perpendicular case for the fields. They're related by the different values of the permeabilities between the two media. Okay, so that's the kind of starting point that we'll want to use to try to find what happens at the interface. Okay, so I've taken the time to draw the little diagrams of what we're going to do here. So how does this go? Well, I'm just going to use the conventions that Griffiths uses in his book, just not to confuse you. What do we have? We have an interface at z is equal to 0. So here the coordinate systems are chosen. So you have x, y, and z. And the whole z is equal to 0 region is separating two different media, 1 here and 2 here. So 2 for z greater than 0. Now, we will consider an incident wave which is coming at normal incidence to the surface. So that means that the incident wave that we have here travels in the plus z direction. The incident waves, electric and magnetic fields, are written then in this form. There's a certain incident amplitude propagating as a plane wave in the z direction at given chosen frequency omega. Okay, so this k1 here is just the wave vector in medium 1 that I have here. So the electric field, we choose our axes so that the x-axis coincides with the direction of the electrical field. That means that the magnetic field is going to be perpendicular to that. So the B field goes in the y direction. And the amplitude of the B field, you'll remember what we just saw, the amplitude of the B field is essentially the amplitude of the electrical field divided by the speed of light in that medium. So that's just E0 incident divided by V1. So what's going to happen? Well, when the wave hits the boundary, there will be a part of it that will be reflected. There will be a part of it that will be transmitted. So for the transmitted, for the reflected and transmitted waves, we adopt the following notations. The reflected wave is going to now propagate in the minus z direction. Okay, so it has a velocity which is of the same amplitude as the incident wave, but going the other way. And now just by convention, we will put the E and R this way, so that once again, E cross R goes this way, so the pointing vector goes this way if you have like positive values for these two things. So there's just a convention here, but it comes out of the equations. For the transmitted wave has an identical form to the incident wave, except for the replacement of the momentum wave vector, of the wave vector here, by that in the second medium. And you remember, so because omega is equal to we had c times k, right? So here we would have v1 k1, and this would be equal to v2 k2. Okay, and v1 v2 are given by the properties of the media 1 and 2. So that's how you relate the K1 and the K2 to each other here. If you have a certain incident K1, the K2 is fixed by this relation here. Okay. So our transmitted wave, once again, has the same form. The electric and magnetic fields are still transverse. Propagation occurs along the plus Z direction like this. So this is our ansatz, our kind of guest form for the fields. All right, so what are we going to need to do? So we need to satisfy the boundary conditions. What we want is to satisfy the boundary conditions, knowing that on the one side, the amplitude of the electrical field is the sum of the incident and reflected one, whereas on the other side of the interface, it's just the transmitted fields. Okay, so what do we have? Let's just go for it. So because we're at normal incident. So at normal incidence, okay, there are no perpendicular components of the fields. Okay, so that's quite simple, because if I go back to our first two equations here, these two equations are trivially satisfied because all these components are 0. So it's just left to fulfill the equations 3 and 4. Okay, so you know, boundary conditions I and II are fulfilled. Okay. The third boundary condition, okay, so if we look at it again, you see it's just that the parallel components of the fields are conserved. So what does that tell me? It just, if I look at the shape of these things here, which I evaluate then at z is equal to 0, and for any omega t that I want, then I will need to equate these amplitudes here. So what does that tell me? 3 tells me that I need to have the amplitude of the electrical field on the one side, so that's the sum of the incident and reflected, that has to be equal to the amplitude on the side 2, which is just composed of the transmitted one. And then the fourth equation, conversely, this one here, you see I've got the mu1 with the b, the mu2 with, again, the b's on the other side. So what does that tell me? If I replace, once again, knowing that the fields have an amplitude which is electrical amplitude divided by v, it just tells me that 1 over mu1 v1, and now if I sum the magnetic amplitudes from the incoming and the outgoing, I just get E0I minus E0 reflected. This has to be equal to 1 over mu2 V2, then just E0 transmitted. Okay, now this is quite straightforward to solve. So what we do is we define a handy little factor, beta, as the ratios of mu times v on both sides. And remembering that the velocity in a medium is speed of light divided by refraction index in that medium, we can just rewrite this as mu1 over mu2 times n2 over n1. Okay, so that's just a handy little factor here. And if we just rewrite these two equations, what you can do is just remultiply by mu1 v1 here, and then take plus and minus of this equation, just do very simple algebra. So what you get is that E0I minus E0R is equal to beta E0T. Okay, so that's this one here. That we've just rewritten with this beta. And now if I just combine this one and this one here, what we can do is we can rewrite the reflected and transmitted amplitudes in terms of the incident one. Okay, so the reflected one is going to be just 1 minus beta over 1 plus beta times the incident one. And the transmitted one is just going to be 2 over 1 plus beta times the incident one. Okay, so that's quite straightforward, right? Now we can ask ourselves, what about the intensity of the reflected and transmitted? So if we look at what we had before, just a little recall. So in vacuum, what we had was that the intensity, which was really the average of the amplitude of the Poynting vector over an integer number of cycles, that was just 1/2 c times epsilon 0 E0 squared. So in a medium, then the intensity is just 1/2, but now I need to replace c by the velocity of light in that medium with then the permittivity of that medium and the amplitude, like this. Okay, so what we can look at is the fraction of the incident intensity in the reflected or transmitted waves. So transmitted waves. Okay, so the this coefficient here, intensity in reflected as compared to intensity in incident, this is just then the ratio of the squares of the reflected versus incident field amplitudes. This is going to be 1 minus beta over 1 plus beta all squared. Okay, and this is called the reflection coefficient. Similarly, the transmission coefficient is just going to be the intensity in the transmitted divided by the intensity in the incident. Okay, so so again, we can just like use the formulas that we have here. In this case here, we need to keep the ratio with the relative velocities and the epsilons here. So that's just going to be in the transmitted, we're in medium 2, so that's going to be V2 epsilon 2. In the incident, it's in medium 1, so V1 epsilon 1, with then the amplitudes of the fields. So there's a T here square, E0 incident squared, and this whole thing, if I just replace V by its value, you know, 1 over the square root of mu epsilon in that medium, I can change this factor here. So this is just going to be, because of the V1 I replace, it cancels against this epsilon 1 here, but only half. So I get the square root of mu 1 epsilon 2 divided by mu 2 epsilon 1, like this. Okay. E0r squared divided by, T squared here, E0I squared. Okay, and this, you know, we've seen it, right? It's just this this thing here. This is going to be 4 beta divided by 1 plus beta squared. Okay, where I've reused the definition of the beta here that we had. Okay. As a quick check, we can do something simple. We can check that R plus T, that is the sum of the reflected and the transmitted intensity, is equal to 1. Okay, and this is the transmission coefficient, of course, right? So T is just the transmission. Okay, so all the intensity in our wave gets either reflected or transmitted, and the particular ratios of the values of reflected versus transmitted coefficient are exclusively determined by the inherent properties of the media. Okay, that is their permittivity and permeabilities. Okay, and that's how you determine it. And this, I remind you, is special to plane waves that arrive at the surface at normal incidence. Okay, so just after this, we're going to do the more general case of the oblique incoming wave.